So this paper is on Vision LLM, that describes how large language model is also an open-ended decoder for vision-centric tasks. Uh, so let's this. So I had a FOMO about using LLMs in Vision. So that is because we as like there are a lot of open-ended use cases in LLMs for text-based tasks, like ChatGPT has revolutionized the industry, and there are a lot more LLMs coming up that are open-ended. But in Vision, we don't see a lot of these kind of things happening, that we give a text prompt and we can get whatever we want. So that is why essentially. So in the existing approaches, there can be a Vision generalist model which can have predefined tasks such as object detection, captioning, visual question answering, grounding. We'll see all of these in some time. So one can be these types of models which can do all of these tasks, but their format of input and output has to be pretty much fixed. You cannot give it natural language instructions. Then there would be visual prompt tuning. So in this, what you would essentially do is that you would give it an image, you would give it what you want, and then you would give it a query image. So in this, for example, object segmentation is needed for the sheet. So you give an input image, the mask that would be the desired output for this case. Then you give it your query image, and this would be the desired output for this query image. So this we saw earlier in one of our discussions as well on visual token matching. So this is that. Um, then this is the method that these guys have proposed, that is Vision plus LLM. So in this, what we do is that give it an input image. We define the task by natural language, and there would be a desired output that is actually defined by the task that we give it. So this is quite flexible in the manner, and follows natural language instructions just like LLM. So here are few what can it do of this model. Uh, So for example, this is object detection. So, you can ask it that I'm giving you this image, tell me what the child is eating. And, draw the bounding box around each of these, give me where the object is present. So the Vision LLM will return you that which object is present where. Then there can be an example of image segmentation, where it specifically highlights all of the pixels that you want for an object. So, for instance, here they're asking for motorbike. So it would provide the pixels in which the motorbike is present. So there are things like so this is somewhat coarse granularity that this paper deals with, but that is essentially the task that it is doing. Then we come to image description. That is essentially, image captioning. So provide a long description of the image. So it would describe the image that white dog is laying on the foldable outdoor cooling pad, things like that. And then there would be visual question answering with some reasoning involved as well. So here is a PC. It asks that if you feel hot, what will you do? So it gives the reason that turn off the fan and other electrical appliances use the disk fan. That is clear. So these are the capabilities that are explored in this model. So let's come to what is the model. So the model essentially has three components to it, and we'll see all of those one by one. So the first component would be a unified language instruction that is designed for both vision and vision language tasks. So vision language task is essentially when you don't require anything very specific to the coordinates of the image. So vision language example would be describe the image in details. That would be image captioning, visual question answering, things like that. And then there could be vision only examples when you require object detection, object segmentation, things like that. So this is one part of the uh, Vision LLM, that is the unified language instruction. Then comes a language guided image tokenizer. So considering this a black box for now, this is a language guided image tokenizer. This takes the image features as input, text features as input, and it would output some suitable tokens for combining both of them. After this is tokenized, it is passed into an open-ended task decoder, uh, that is an LLM. Uh, so in that, this language-guided image tokens are passed, and the input text is passed. Yeah, so that are three components essentially, and they give you the desired output. So coming to the unified language instruction, uh, so for vision language task, the instruction can be like the image, please generate a caption for the image. So this image in these brackets would mean that we are placing the tokens here that are obtained from the language guided image tokenizer state. So we are placing the tokens here. And for the second question, we are placing the tokens for the question here. So this was for vision language tasks. For vision only tasks, so there can be some conventional tasks that are object detection, object segmentation, things like that again. So how they're passing it is that they provide a class and they provide coordinates to with respect to each of the vertices. So this is the format that they use for vision only tasks, and the image is image. That is the same as in the previous thing. Yeah, so the task description essentially conveys the intended task to the language model, and they have used LLMs to generate a variety of these instructions. So the fixed thing in these is these format, that is the object class and the coordinates format, the image. And they would ask an LLM just like Chat GPT or GPT-4 to paraphrase it to give it a variety of instructions. So everything doesn't matter, obviously. So that was the first component. The second contribution is the language guided image tokenizer. So essentially, they treat images as a foreign language. And in this tokenizer, all in all, what is happening is that you pass an image and you get the tokens that are suitable to the LLM. So how is that happening is that they pass it to an image backbone. So this image backbone, they have used two of those. One is Resonate, our classic one, and one is Intern Image. That is quite a new architecture and based on CNNs. And so this image backbone would give us the visual features, and these are calculated at four different scales to aid with smaller objects as well. Then after that comes a text encoder, which gives us the language features. So this can be our classic BERT. So these were parallel steps. Then what is happening is that using cross attention, the language features that are obtained here are injected into the visual features that are obtained here. So we obtain multi-scale language-aware visual features. So I hope this has quite a few terminology, but each of these I believe would be clear. Multi-scale corresponds to these four different scales language-aware because we are using cross attention to inject the language features and visual features. So after this is done, we use a transformer-based network with n random initialized queries to capture the high-level information of images on top of these features that we obtain here. So for this, they have used an architecture called deformable deformable DETR that we see in some detail shortly. So next would be that independent of input resolution, and it is informative with respect to the language prompts. So since we are using 4 different scales, so it is relatively independent of the input resolution of the image that we use, and it has information with respect to the language prompts. So the tokens that we receive after final step are in this format. So EI corresponds to each embedding and LI would correspond to positional encoding. Okay? Assuming that is clear. Uh, so yeah, so this is one of the backbones that they use. We won't go into very much detail over here, but taking this, the essence of this would be that global attention, it is not very computationally efficient because it goes throughout the matrix to calculate the weights. Then there can be local attention. Again, this does not have long range dependence. That if it wants to calculate it with something over here, that then it is restricted to do that. Then uh, for a very large CNN again, it would lose the adaptive spatial aggregation. So, it is calculating for the whole of this space at once. So, like we do that, we first gain edges, then we gain some contours, things like that. So that spatial aggregation sort of thing is not happening. So we might lose on features. So what intern image does is that it essentially employs a attention kind of mechanism, but it chooses to as to where to give the attention. So this is learned as well in this type of backbone. So it has all of these three features. It has a long range dependence as to as in it can calculate attention with far off uh, pixels. Then it does have adaptive spatial aggregation because it calculates for small patches. Then it is also computationally and memory wise efficient because it does not calculate for all of the patches in the image. So briefly looking into deformable DETR, that is the architecture that they use to combine the uh, to get multi-scale language aware visual features. Sorry, to extract the tokens after you input the multi-scale language aware visual features. So in this network, what essentially happens is that you give it a backbone. That there is a CNN. You also input the positional encoding. These are combined in some manner, and they are passed to a transformer encoder network. And then there are object queries. So these are passed to the decoder, the encoder output and the object queries. Then the decoder generates its output, and then those outputs are passed to feed forward neural networks to give all these predictions for class box if there is any object present, things like that. So this was DETR. So what deformable DETR essentially enables us to do is somewhat similar to what we saw in intern image, that it gives attention to far away objects. Matlab, it is not a fully dense kind of attention. It helps us make the attention sparse. And also, inherently, we can use feature maps with this that we calculate for 4 scales of an image. So that's why the cross code over here. After that, we obtain multi-scale feature maps. Then we pass it similarly to a decoder, and using object queries, we can decode and get the bounding boxes. So this was about the second part of the Vision LLM. The third part would be the LLM-based open-ended task decoder. So for this, the LLM that it uses Alpaca, that is a fine-tuned Llama model. So there are few disadvantages with Alpaca. So the first one would be that it has few digit tokens, thus enabling it to locate objects by numbers. So although this is somewhat better for calculation purposes, but when we are dealing with multi-digit numbers, so for here it would not be very efficient, and it can easily generate some unexpected outputs. So then there are multiple tokens for category name, which would lead to inefficient classification. So for example, if I tell the model to classify or maybe detect wherever a person is present. So I'm inputting person as a class. So it would tokenize the word person into different tokens as well. So multiple tokens correspond to the category name. So this is also inefficient. And the third thing is that it is a causal kind of model, as in text-based things. It gives you a reason based on a cause, which would be inherently inefficient for visual perception tasks, as in it has not been trained on these kinds of tasks. So we need to do that. So the solutions that the authors propose are that to deal with this few digit tokens, they take discretized location tokens. So what they do is that they take a positional encoding from a positional token for -512 to +512. So this is a hyperparameter that we see in ablation studies later. But in their model that they will be releasing, this is the number of tokens. So in that way, essentially an image is divided into bins. So in this case, it would be 1024 bins. Then there are category name tokens. So for each category, they assign a token. So for example, person could be C0, bicycle could be C1. So that word is not further broken down into tokens. Then third thing is that the output format of this LLM is query decoding, as in we provided queries in the format in a very specified format, and then it decodes those queries. So when we define the task, what the LLM is first doing is that it is parsing the instructions to form a structural output. For example, we were seeing, right, that unified instruction is given. So from that, it is parsing. Like there is a class token, then there are positional encoding tokens, not positional encoding tokens, discretized location token. So this POS would mean that the task is on image captioning, so things like that. So that way, it generates some, structural queries for what to pass to the decoder. So that was about the model description. Coming to the experimental details. So they evaluate their model on 5 vision-centric tasks. These are object detection, instance segmentation, visual grounding, image captioning, and visual question answer. So I think all of these would be pretty backend except for visual grounding, that would essentially mean that you are asking the model to locate an object that you are giving. So, for instance, you ask that, say, where is an apple present in this image? So, you know, the model localizes that. Then talking about the datasets they use are COCO 2017 for object detection and instance segmentation. Then for visual grounding, they use these three datasets. Then for image captioning and visual question answering, they use these two datasets. For testing, for captioning, they use uh, a test split of this COCO dataset. And for visual question answering, they do a qualitative assessment. The rest of them, they are not very specifically mentioned, but I'm assuming this would be a split of each of these datasets. So for image backbones, they have tried ResNet, intern image, which as I previously mentioned. For language guided image tokenizer, BERT piece was used as text encoder and deformable DETR for the high level information, the tokens that we generate. So the number of queries that they use for deformable DETR are 100 in number, and the encoder decoder layers are 6 each for this. The LLM model that they use is Alpaca, the 7 billion model. So the training that they do is in two stages. So in first
Hi,
stage,
hi, 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 Ayush.
yeah, yes,
Can you go back to the data set again? Just the slide, just for a minute. Yeah.
yeah.
Just I want to, just okay. Okay, thanks.
Yeah. So the training happens in two stages. So in the first stage, the parameters for the LLM are frozen. So the LLM is that Alpaca 7G model, and the rest of the models are trained, and they are, the weights were used as pre-trained weights, uh, as in the initialization was with pre-trained weights. And so for the first stage, they mostly perform the object detection task with some random object categories and task descriptions. So this random task descriptions we talked about how they generated. That was with LLMs. And in the second stage, the visual backbone is frozen, as in uh, the ResNet or intern image that we use, and there is a unified supervision of multiple tasks to train the LLM. So that would mean what that would mean is that uh, we are training it for multiple tasks at once in the second stage. Yeah, so now we are on to the results. So for object detection, they were pretty close to the state-of-the-art object detector, and it outperformed the vision generalist model. And so a particular advantage that it has is that it can make multiple predictions in parallel because it is following uh, query uh, query decoding kind of as in for multiple object types it can predict in parallel. So for visual grounding, so this essentially conflicts with object detection. So we might see a slight degrade, but the results were also comparable to other models. Coming to instance segmentation, so the way they do instance segmentation is that they ask the model to predict a polygon of 8 to 24 vertices. So this is a parameter that they give in the prompt itself. So for example, I'll ask the model to predict it in 8 vertices, a polygon of 8 vertices. for instance segmentation. So the results for average precision at 50%, 50% were comparable to other models, but the results on 8075 were poor. So this could be due to discretization of the location tokens and polygonization, as in we are dividing it into vertices. And for the image captioning task, the results were decent, not really exceptional. So this is the table. So in this we can see that for open-ended decoder format, we have slightly degraded results than the close-ended thing. So what that would essentially mean is that it is trained on only one task. So the results for that are slightly better, not very much. Uh, yeah, so for captioning, the results were not that impressive, but for other tasks, they were pretty. Ahead. So this is a study that they performed that object level customization. So for this, they vary the number of classes that they want to predict. So in this, with the number of classes at 20, they get decent results, but they are not very much varying essentially. Yeah. So output format customization. So this corresponds to the instance segmentation task. So varying the points from 8 to 24. This also does not give very bad results. So of course there would be changes when we change the number of points and see. But this does perform. Uh, so these are the ablation studies. So this is the effect of text encoder in the language guided image tokenizer. What they tell is that for object detection, BERT is not as necessary, but for instance segmentation, BERT is really much necessary. Yeah, and this would refer to the freezing of parameters of BERT. So this also degrades the performance quite a bit. Then there is image tokenization method. So with average pooling, they get much worse results than using the method that is in DETR. Then there is the effect of number of bins. So number of bins for the position, the location tokens that we use. The double of that, not the double of that, but the number precisely, but negative to positive. So that's why this happens. So this was the standard 1025, and when they double it, the performance does not improve. So they fixed the number of wins at 125, that is taken from minus 512 to plus 512. And with decreasing the number of wins, obviously the performance deteriorates. So this was about this paper. Uh, so I was looking into a few more papers for LLMs and vision. So one of those is visual instruction tuning. So what they do is that they take an image that is passed through VIT kind of architecture. So for this, basically, they use the clip embeddings. So these embeddings are then converted to embedding that is suitable to the language model. So this ZT feature vector is multiplied with a projection W. So this is also a learnable matrix. They multiply it with this, they get HV, which is essentially the same dimension as of any token for this language model. And then there is a language instruction that is tokenized and passed. So here goes your image and here goes your language instruction. So that is essentially how they deal with it. Uh, so this is a chatting kind of thing. So they try to create something similar to C. Then there was another paper that is also somewhat similar in its approach. That what they do is that they pass it through VIT and Q format, and then they pass the output of this to a linear layer to make it suitable to the LLM that they're using. So I feel that the essence of both of these approaches is pretty much same. Uh, yeah. So that was about the paper and the discussion LLMs and vision. And now we can take up any questions or as
Ayush, have you observed any major difference in image encoder in BIT and this method?
the image encoder. So there is not an encoder per se in this. Uh, so in VIT, you would pass patches, uh, patches that are flattened, and they are passed to the encoder. Rather than doing that, what you do in this is that you first pass the image through CNNs, and you get a set of image features. So after that, the things are pretty much same. Matlab, as in to the encoder, the input is different in BIT and DETR. As in this, you are inputting image features, but in VIT, you are inputting the patches of an image. So that is the difference essentially.
Uh, so Ayush, you mentioned in one of the slide that there is some discrete localization tokens. So that
Yeah.
is also some kind of patching only, I think, or is it something different?
Uh,
Yes, this.
so this is uh, creating the whole image into sort of bins so that your model predicts one of those bins. So this is
So
on the output side of the things.
so bins and patches are different, or is it somewhat similar? Slightly
Yeah, you
confused.
can assume that both of these are essentially dividing the image space into grids, essentially. But patches in VIT are on the input side, but
Yes.
here you are predicting one of the tokens. So these are on the output side of the thing.
So for input, we don't have to divide it. For the when we get the output, we will have somewhat grid structure, right? Out of which one will be
Yeah,
selected. Okay,
right.
okay. So
Also, there
also
is a difference in the dimensionality. In VIT, there are only 16 patches. Here, there are quite a few.
okay. And one more thing that
Yeah.
I was not very clear about this grounding, the visual grounding and instant segmentation. So what is the difference? Like it sounds similar because if you say that where is the apple in the image, so if
Hmm.
we want to segment it out, it would do under segmentation also. So what
Okay.
is this?
Yes. So let's look at
Yeah, example
one.
would be great.
So while I find that, uh, so one was visual grounding, right?
Yes.
In that you are trying to localize it in a bounding box, but in image segmentation, you essentially want to classify each pixel as it as if it uh, belongs to that object or not.
Okay. So then in object detection also we'll have bounding boxes only, right? So how is
Yeah,
this
right.
different from how is visual grounding is different from all others?
Yeah, yeah.
I think visual grounding is doing based on a natural language query,
Yeah, yeah,
unlike object detection and segmentation.
yeah.
Okay. So but
So,
he mentioned that the queries are more or less fixed for all different tasks. So like,
uh, so this part is more or less fixed. That is the highlighted part. You are giving it the classes that you are trying to predict and the
okay,
output format. But the rest of the things are, and this image thing, this would also vary depending on the language, of course. But
okay,
the
like
language that we are using, that is very much variable. Like I discussed, right, that they were trying to augment sentences using that.
okay. So like while you went through this paper, was there any mention about hallucination or anything? Because if let's say I ask it to detect some apple in the image, is there a chance of hallucinating, or is it more accurate as compared to the other solutions? Was there any such mention in the paper?
Uh, Hallucinations, I don't think would happen in the object detection as much, and the results are also comparable with the other model. But in visual question answering, there could be a this chance of hallucination, and in captioning as well. So
Okay.
in detection, I don't think there would be hallucination.
Mm.
But we can only tell when we actually try it. So the model, the GitHub repo for this is there, but they have not yet released the model and the demo.
Okay. And here this for instance segmentation, this AP75 is also somewhat lower than AP50. This is also somewhat counterintuitive, right? Is there any
Yeah.
specific reason?
So there is somewhat more change in AP75 when compared to other models.